green square there, and flow. Good. Hello and welcome back to Calculus 3. We are starting chapter 14 on vector fields, and we are going to take a look into everything we learned so far in mathematics, especially in Calc 3, put it together. Well, we'll take the integration and parametrization and vectors and put everything on a pile to come up with the mathematical framework that we can use to understand electrical field, magnetic field, gravitational field, but also to understand how winds work and fluid flow, airflow, how to get the airplane into the air, and so on. Aerodynamics, right, of the cars and things like that. So it's essential for your design as engineers. So the better you know this, the better. Plus this new trend that on the interview they ask you things if you are applying for a job in one of these high profile companies. They generally pick stuff from here actually, because this is what you have to understand and you have to use if you want to design planes, design, I don't know, cars and stuff like that. So we start with understanding what the vector field is, few definitions, and compute few examples. So this is the introductory section, so it's kind of short and sweet. You know what the vector entity is. So you have this arrow, right, that starts at a point, stretches, and it has its magnitude and it has its direction theta. So that's a single vector which has magnitude and the direction. Now what would be field of vectors called the vector field? It will be a whole bunch of these guys all pointing and doing something, right, that would show some kind of a flow. So we can see that the paths through this field would be like this. I hope you see that, because these little vectors guide which way the particle could move. So think of a particle accelerator. You have some kind of a particle inside and you apply insane magnetic field there. It will propel, right? And the way the magnetic field points as the way that the particle is going to go. Think of the fluid flow, the river flow. Think of each individual molecule of the river of water that is there moving, where these little vectors are attached to each single particle. These little vectors fill all of the space. I can't draw all of them because they will all be on top of each other, but at each point of space there is one vector to be drawn. You have the air conditioning here in the room, you can hear it now. In 3D it pushes the air. You can turn the fan on and you will have the vector field push forward. So you can actually see and feel these. But then you have a gravitational field, electric field, magnetic field, and so on. So some you can see and feel, the other ones you can't. That doesn't mean, yeah, you can. You don't really feel it. You see the evidence of it. So what is the vector field in 2D? So vector field in 2D. So let F and G be defined on a region R of R2, which is the 2D. So a vector field is a function. Vector field in R2, which is right, is a function f with the arrow on top because it's a vector that assigns to each point in R a vector f of x, g of x, sorry, f of x, y, g of x, y, you can write that the vector field f of x, y is equal to the vector f x, y, g, x, y, or you can just use the component form, so you can write fxy I plus gxy, so all the notation remains the same. J. Also going to say that the vector field f is continuous and differentiable on R if both f and g are continuous and differentiable on the same R. Ta-da! No. Definition of a function. Yes. Function is a rule which assigns to each x in a domain a unique y in the range. Same thing here. Vector field is a function which assigns to each x, well, to each point, right, in domain, which is to each x and y point assigns a unique vector, which is described with f and g. So yes, this is the definition. So this is the higher creature. Very good. Yes. Props to you. Examples. So we can't really draw everything, but we can draw some of the vectors. I already talked about that because remember that each point in space will have a vector associated to it. And there is no way that we can draw all of them. Well, we can draw some to get the idea of how the entire vector field behaves. So here is the vector field, let's say 2x to y. So how would something like this look like? We are going to remember that this is F and this is G. And say I want to draw this. I'm sorry? What do you mean? Oh, in that way, yeah, sure, you can represent, yeah. But again, all right, so let's see. What's happening at point 0, 0? What vector is attached to a 0, 0? Yes, so I forgot these arrows. So the vector 0, 0. So 0, 0 vectors there, so I'm just going to draw a big fat dot at 0, 0. It's a 0 vector. Now, what do I have at 1, 0? So 1, 0 is right here. So vector field would be twice the x, which is 2, twice the y, which is 0. So I have 2, 0. So the vector 2 units long. Maybe I should, let me use red. Now what do I have for negative 1, 0? Negative 2, 0. So negative 1 is right here. Negative 2, 0 is a vector here. How about 0, 1? It will be 0, 2 vector. So that's this. And then by process, right? Same. Have for 0, negative 1, it will be 0, negative 2. Great. Now, how about if I have 1, 1? It will be 2, 2. So it looks like it's going to look like this. We call fields like this radial fields. Can you all see that the point at the origin is radiating out? It's like a source, like sun, let's say, right? Radiates out. So radial field. We will also have rotational field, which turns. So you can have radial field, rotational field. You can just have flow. You can have shear. You can have all different types of field. Now this is, I'll show the picture in the book, obviously much more detailed and better. Look at that. Right. Now, no. Linear combination. What do you mean? But if you take a look at both f and g depend on x and the y. That function, they change to be nonlinear as well. You can have anything there. You're computing values. Let's take a look at more examples. So technically what you do, you take a look at what the vector field is given as, which is f comma g, and you use input points to compute the value for the vector. Here is the 0x. So here's your F, here's your G. Let's see how this looks like. Going to draw XY, which is the R2 surface, right? So this surface is R2, 2D. So I start with 0, 0. At point 0, 0, vector field has vector 0, 0. So I just have a dot there. How about 0, 1? Still 0, 0. Very good. How about 0, 2? Okay, so it turns out that along the y-axis, they're all 0 vectors. There is no motion, there's no flow on the y-axis. But how about if I go 1, 0? Why? I turned off the syncing. Why is this still? Oh, it's still syncing over here. I don't know why. Didn't I just sign out? So yes, the first one better always be 0 because the first one in the vector is always 0. The second one is whatever x is. So at 1, 0, which is here, I have a vector that goes up 1 unit like this. What do I have at, I don't know, 2, 0? 0, 2. How about the 3, 0? 0, 3. Then 0, 4. Now we need to understand that that's what's happening here. Right? You see that the more outward you are, there is stronger push. Now what happens if I have negative 1, 0? It looks like this. And then like that. This one is known as a shear field. Can we see that? So if I was able to stretch this, I have to push the top this way, the bottom that way, and create a parallelogram out of it, right? Can't do it, but that's what it is. Yes? It's not a fixed point, it's like a fixed line. That one doesn't move. Should I say that it's full of eigenvectors? Oh. After a transformation, eigenvectors are vectors that are not changing under transformation. People don't understand that. You go eigenvectors and eigenfunctions, it's just like, oh! But the transformation. Yes, but it's kind of cool to learn all of the main jargon and be able to repeat the problem that is done, but what it actually means and how it's used. So in terms of the last section, the one that we just did, 13.7, we had a transformation which changed xy into uv. the eigenfunction would be the one that once you transform xy into uv, the uv looks the same as xy was. So it didn't really change under the transformation. The region changed, and some other stuff changed, but the function stayed the same. So there's a lot of stuff you have to learn about that. Anyway. This is a cool one. That's really cool. So let's see. What's happening at 0, 0? One zero. What's happening at 1 0? Still 1 0, right? Yeah. Y 0. So what happens at 2 0? 1 0, exactly. So all of these are like that. Actually, this is, my drawing is really bad. Let me try to do a better job with this. Hold on, Chewbacca, I'm getting there. So I'm going to use 4 units as 1. So now when I draw the flow, we see that the flow along x-axis is this long. Great. Now let's see what happens at, if I move a little bit away, what happens at 0, 1? What happens at 0, 1? 0, 0. Okay. And what happens at 0, negative 1? Same thing because it's squared. Very good. Appears there's no motion. So anytime when y is either 1 or negative 1, there is no motion there, right? And let's pick other values. How about 0, 1/2, which is right here? What happens there? 3/4 and 0. 3/4 and 0. That's 3/4. That's how they look like. So there are 3 squares long in this case, along this line. And therefore it has to be symmetric, right? Because of the y squared. Now how about what's happening at the quarter? 0 and a quarter. Which is here. So 15/16 and 0. So they look like this. And then symmetric. Great. Now what happens at 3/4? Nine over 16. 1 minus, so that's 7 over 16. So that will be this one. What is this? It's a flow through a tube. Very good.
So the flow is strongest in the middle?
Yes.
Because of the wall?
Why? Friction against the walls. Yes. So this is, and now do this in 3D, you get the blood vessels. Or you get any type of fluid flow through any kind of tube, which is the, right? Because as you have a tube over here, anything that it's, when you push the water through, right? The water that is close to the walls has friction, right? So it's going to be moving slower than the one in the middle. That's how flow looks like, and this is a 2D representation of the flow, but you can have a 3D flow. You can understand how the fluid moves through the.
That's why the formula for what is it, blood going through the body, isn't it? Viscosity times distance over, no, times 1 over 1 minus distance squared.
Yes, 1 minus distance squared, and you can see that 1 minus distance squared on over there. Yes. What happened? Resistance again. There is a resistance here on these edges. All the flows are the same. Joe.
When you're drawing it, like the space that you're putting in between the tip and the tail of the arrow, you're just drawing that to show like the size of the exact. Like you could shift all that to the left, right?
Yes.
As long as the arrows are the same
Yep.
size.
Because the next arrow starts right there, and the next arrow starts right there, and the next one starts right there, and it's just. Well, you can start drawing these anywhere you want. That's technically what the question was, or the statement was. It's just I'm trying to kind of organize it so we can see there is a flow. So I started everything on axes, right? So it's easy to see this cone over here, which is the one that kind of pushes, and you see that the strongest flow is in the middle, and then it kind of dies off towards the edges, and then there is no flow at the edge. Flow.
So if we put like some object in there, it would experience like some force.
If you put, yeah, if you want a blood clog right here. If you put a blood clog right there, then that will obstruct, this equation would change, and these vectors over here would have much stronger magnitude because right, stronger magnitude is what's happening. You have to, heart is pushing, right? So it's like a pump. So that's constant pressure, and we evolved such a way that it's balanced to deliver right amount of blood through all, like, even the longest of the extremities, right, all the way to the tip of the toe, right, from the heart. That will be the largest distance to go. So when you calculate all of these things, right, there is a blood clot, right? Let's say you did not eat cookies, so obviously it starts forming. Then the blood will be pushing at the same, right? The part will be pushing at the same pressure, but now there is less of the area, right, or the volume to pass through. So if that happens,
Well, I meant like a tiny
come on.
particle. Like if you put like a particle in there.
Come on, just close it.
No, I don't want to know what it does to the field. I want to know what the field does to the particle.
You know how when you have an IV in your arm?
I like that answer.
You know how they clamp the IVs in your arms so they limit the amount of space that you have in it to limit the rate of blood flow going into your body? It's that. But using the outside wall, you're using your blood flow rate.
Yeah.
Going to that.
So if there is a clot, there will be just that the vector field will be stronger. There will be more force in terms of pushing through. So that's why the blood vessels that's why the blood vessels first play. Yes. Well, I see that's where the critical values, like put 1 minus 1 is 0. Now, technically, mathematically, what you get here, which is what we don't have actually if you are observing the blood vessel, but mathematically, if you go past this, they will just go like that, which goes. So you can actually restrict if you want to, right? You can restrict y between -1 and 1 if it makes you happy. I'm not sure if they restricted that for us already. Did they?
On the outside.
They did. They did restrict. I didn't write it. All right. So you can calculate technically anything with these. So as long as you can, right, plug in x and a y, you pick a point. That's going to be your x and y input. You carefully compute the vector and then just plot that vector. So it's not that difficult. Good.
So if we had like a different surface on the outside, I guess, that applied more friction, would that change the formula that was used?
Yep, everything changes the formula. Because as soon as the field changes formula, has to change to accommodate it. So there's a one-to-one correspondence between the picture you get and the vector field input. All right, so definition for the radial field. So in this particular definition, P is a real number. We did have already, we already had the example of the radial field earlier. But that example, well, it's not 3D, but let's just cut the sun with a 2D plane and look at all of the sun's radiation along that plane. We understand if you look at the sun, this vector field looks like this, right? So you see that the further away you are from source, you are experiencing stronger radiation, which is not true for the sun, right? So this would not be a good radial representation for the sun, because obviously the field is getting stronger as you're getting further away. For the sun, it should be something like this, where you have the strong one and then it's becoming weaker as you are further away. That's much better in terms of, you know, what we need. And so on. So this would be more like a sun, and this is not a sun-like. So we are talking about this f, function f, being some kind of a scalar function. So it doesn't have to be just a number. It has to be a scalar value function, but in order for this to be a radial field, but you can accommodate both of these situations. So f could be times the vector r. Did I put the vectors over here? No, I didn't. Great. There we go, much better. Where f function. So here are more examples. For instance, vector field given as, don't forget the arrow above f, xy divided by the square root of x squared plus y squared, or right. So that's another example of the radial vector field. Yep. So understanding the vector field, you will see when it looks like this, it's a radial field. If it looks like this, very good. It's rotational because you can see rotation going this way, right? So once you start drawing these things, practice a little bit, you will be fine. And then you have all of this in 3D as well. So vector field in 3D is the same deal. So vector field XYZ is fxyz, it's a vector, right? Gxyz and age xyz. You can do a age ik if you want to, and then the radial one, it's the actual 3Ds for the sun, you can use that and so on. So that's the regular one, and the radial, same deal as before. You have the radius, which is the vector, times the scalar function, which makes them larger or smaller, right? There's no way I'm going to draw any of these 3D ones because they take a long time. So here is the textbook. We hopefully see the flow through the cylinder. You see the larger arrows, vectors in the middle towards the center, and the smaller ones towards the edges. Again, the strongest flow is always in the middle of the tube, of any tube, and then as you start restricting, it goes even faster. You know that, right, from playing with a hose, right? And then just a random vector fields here. Here's the radial one. You can hopefully see the source in the middle and everything just radiating out. That's the sun. So now again, this is not the sun one because again you have the shorter ones inside and then, right, but this is like the inverted sun, right? The further you are, the stronger it gets. Yes,
What kinds of things would have smaller vectors and stuff like that?
Magnets?
No.
But magnets pulls close to the inside, right?
It's stronger pull. Yeah, but the field is.
But the field is weakening. We're talking about the field.
Yeah.
So the field is weakening.
The field is
All of the stuff that we're doing is the opposite of this.
If you pull something.
does anything exist
You make that face too big.
that a lot of fish that field is
Thanks.
It's not like a ball in the pool.
I'm just gonna say this one.
Love. It's the more there is, the more you want. There you go. I don't know. I can't come up with any example right now. So deal with that one. I don't know.
I feel like this is really just like a lot of meteorology.
Oh hell yes. But then also temperature. They should have a really cool temperature distribution over here somewhere. There was one I know somewhere. Let me just.
This is pretty cool.
Oh yeah, it was on the first page.
I'm probably gonna be seeing this for that.
There you go. So yeah, this is the hurricane. Hurricane Floyd forecast.
Oh, hey.
So you see, here is the 2D, what's happening on the ground, but then you have which way the vector fields go on top. So there's like a whole bunch of stuff. This is probably some kind of temperature distribution. This is the magnetic field.
What year did that happen?
Do what?
What year was Floyd?
Something I don't remember. 19.
You have technology in your tip. Oh, fingers. All right, good. So hopefully you guys will look at this stuff and practice drawing these. Now, the last part is so gradient fields and the potential function. All right, so do you remember what the gradient was? Yes. So the gradient of the function f was a vector when you had your derivative of x prime, y prime, and z prime, let's say, for 3D right away. So the major conclusion here is, so gradients generate vector fields. It is useful information because any function that does this is called a potential function. And we have a procedure how to find the potential function when it's given. So here, vector field is equal to the gradient of phi, and we're going to call phi potential function, which means that the vector field is partial x, partial y, partial z from the potential function. And we are going to learn eventually, I believe in 14.3, we're going to learn the procedure of how to find potential function. And that will be recycled later on in your differential equations. If you haven't taken differential equations yet, if you did, you saw that calculation under a different title in DFQ class. It was called exact equations, and we used the exactness condition. Yes, that's so. Chapter 1. You do Calc 1, Calc 2, Calc 3, then differential equations, and then linear algebra after that. That's how it's done. Yeah. Preferably finish all of that by the time you're done with high school, right? All right, good. So just practice a lot of these guys, and I'll see you in 2 days, and we'll do more work.